All right, welcome to this explainer. Today, we're diving straight into a foundational mathematical concept that hides one of the deepest mysteries in human history: prime numbers. It's an idea so profound, it literally stumps the greatest minds on the planet right now, despite having been studied for thousands of years. So right out of the gate, I want you to think about this. What is the most unbreakable code in the entire universe actually made of? You'd probably guess, I don't know, some insane quantum mechanics or hyper-complex software algorithms. But actually, the answer lies in something deceptively simple: prime numbers. To figure out why your entire digital life depends on them, well, we've got to understand what makes these numbers so uniquely powerful in the first place. Section 1. The atoms of mathematics. The fundamental theorem of arithmetic. Okay, so to really grasp their power, we need to quickly look at what primes actually are. By definition, a prime number is a natural number greater than 1 that is not a product of two smaller natural numbers. The really crucial point here is this illusion of simplicity, right? It's completely mathematically stubborn. It's evenly divisible only by 1 and itself. It just stands totally alone. Just compare primes like 2, 3, 5, 7, and 11 against composite numbers like 4, 6, 8, 9, and 10. Composites can always be factored down to their base DNA. I mean, 4 is literally just 2 times 2. 6 is 2 times 3. So composites can be broken down, while primes, they're the unbreakable foundational blocks that build absolutely every other number. Basically, every integer larger than 1 is either a prime itself, or it can be factorized into a totally unique product of primes. Moving to section 2. Was 1 a prime number? The historical identity crisis? Now, this foundational definition actually builds into an incredible historical controversy regarding the number 1. Get this, the ancient Greeks didn't even consider 1 to be a number at all. Then, fast forward to the Renaissance, mathematicians finally started treating 1 as a number, and eventually a lot of them included it as the absolute first prime number. Christian Goldbach listed 1 as a prime back in the 18th century, and mathematical lists literally kept including it all the way up until 1956. It's absolutely fascinating because this caused massive mathematical headaches and forced us to constantly rewrite the rules. So why did we finally decide once and for all that 1 is not a prime? Well, the answer lies in the fundamental theorem of arithmetic. This states that every integer larger than 1 can be written as a product of 1 or more primes in a unique way. If 1 were still considered a prime, this entire theorem would completely collapse. Why? Because every single number would have multiple infinite factorizations. Like the number 6 wouldn't just be 2 times 3, it'd be 2 times 3 times 1 times 1 times 1, just going on forever. So to keep our mathematical building blocks unique, 1 had to be kicked right out of the prime number club and put into its own special unit category. Section 3. Proving the infinite prime. Euclid's brilliant logic. So how do we actually know that primes don't just eventually stop? Well, around 300 BC, the Greek mathematician Euclid used this incredibly elegant piece of logic to prove that prime numbers go on forever. Here's how he did it. Step 1. Imagine you have a finite list of every single prime number in existence. Got it? Okay, step 2. Multiply them all together into one massive, giant number, and then just add 1. Step 3, if you try to divide this new number by any of the primes on your original list, it will always leave a remainder of 1. What does that actually mean? It means your new number is either a brand new prime itself, or it's divisible by a prime that wasn't on your list to begin with. So Euclid basically proved that you can always generate a new number that isn't divisible by any prime on a hypothetical list. Therefore, primes are infinite, period. Which brings us to section 4, unsolved mysteries and gaps. The limits of human knowledge. But here's the crazy part. Despite knowing for a fact that primes are infinite, we understand shockingly little about exactly where they appear. There is still no simple, reliable formula to predict a prime number. Honestly, they pop up like weeds among the natural numbers. And this leaves us with a staggering list of unsolved mysteries and conjectures that completely overwhelm the greatest minds working today. I mean, we have the twin prime conjecture, which guesses there are infinitely many prime pairs that differ by just 2, think 11 and 13. There's Goldbach's conjecture, which states that every even integer greater than 2 is just the sum of 2 primes. And then, of course, there's the Riemann hypothesis. This is a literal Millennium Prize problem whose solution carries a $1 million reward dealing with the deep distribution of these numbers. These concepts are so easy to state, but they have completely withstood proof for decades, some for centuries. 4 quintillion. That's a 4 with 18 zeros. To put this into perspective, we have used brute force modern computing to verify Goldbach's conjecture up to 4 quintillion, meaning every single even number up to that point is indeed the sum of 2 primes. Yet, in mathematics, computation is not a proof. Because primes are infinite, we still don't have a formal mathematical proof for it. It could be that the very next number we check breaks the rule, and we just don't know it yet. It's wild.
Section 5. Prime Patterns and Cryptography. The foundation of digital security.
Now, let's ground all this abstraction into your everyday life. We usually think of the distribution of primes as just random mathematical chaos, but when you plot them on a 2-dimensional grid called the Ulam spiral, something magical happens. The numbers spiral outward in concentric squares, and visually, primes strangely cluster on certain diagonals. It's like a giant puzzle. They aren't purely random at all. They heavily suggest a hidden underlying structure. It's a tantalizing pattern that mathematicians are absolutely desperate to decode. And why? Because if they do, the consequences are literally enormous.
This brings us to a crucial real-world application. Modern public key cryptography and systems like RSA rely entirely, and I mean entirely, on the extreme difficulty of factoring massive numbers into their prime components. Remember earlier when we said that every number is made of prime building blocks? Well, it's super easy for a computer to multiply 2 giant prime numbers together. But if you only give a computer the resulting massive composite number, it is incredibly difficult and time-consuming for it to work backward and figure out which 2 primes created it. Because we lack a simple formula to tame these primes, this very mathematical limitation is exactly what keeps your bank accounts, your private emails, and your entire digital life perfectly secure.
Which brings us full circle to a somewhat terrifying realization, right? If someone finally cracks the Ulam spiral, or, say, solves the Riemann hypothesis, and discovers the hidden formula for predicting prime numbers, will our entire secure digital world instantly crumble? It is a truly fascinating paradox. So I leave you with this thought to take away from our explainer today. Are we entirely dependent on our own mathematical ignorance to keep our modern world safe? Until we finally solve the prime number mystery, the answer might just be yes.